Okay, so I'm sure you can all see my screen from now. I'm going to go on stats. Welcome once again to today's session. I think we have 1 hour 20 minutes ish to just go through how we can solve the systems of linear equations using Python. And I think now we are diving more into the use of the libraries and not just the mathematics the raw Python code. Okay, so yeah, so before we even begin, let's just see what we are supposed to cover today. Right. So yeah, we're going to use the Gaussian elimination method. We're going to use the matrix inverse method, and yeah, check out the different alternatives for solving linear systems and why we choose to use some of them and not the others and all of that. So yeah, as we go on, we'll see. I'm hoping I'll be able to capture everything and you'll be able to understand. Yes. Okay, so first things first, as usual, we import libraries. Here we have NumPy. Because we are doing numerical stuff, we need NumPy. We have the matplots library because I'll be doing be showing some of the stuff geometrically, visually, so you can understand what's going on when you do the transformations and all of that. And these here is just parameters to keep our values in a particular significant figures, right? So setting this to 4 significant figures, and the plot size is also just so that the graphs are a bit larger and readable, since I'm like sharing my screen and all that. So you can do without them, but then it's just to configure what I'll be using over here. Right? So I think before already done the theory, so I'm not going to spend much time doing that. But then this is the main equation that we'll be dealing with. Ax equals b, right? A is the matrix that's going to contain the coefficients from our system, and then x is the vector of the unknown vector that we'll be solving for, and b is the resulting vector, right? From the left hand side, that's the ax, right? Or our target vector, where a times x must land. Okay. So first thing, we define our matrix, which is A, and this is representing it as a matrix form. So this is a 2 by 2 matrix, and we specify the data type over here to be floats, which you can also do without. In case you're having matrix values that are like decimals and all, it's good to set it to specify the data type. If not, you could leave it there or not. And then we have integers, so it's still going to treat it as, I mean, it's going to work either way. So, but then this is just specifying data type as floats, right? And we set our, we also define the vector, which our vector b, right? It's -2 and -4, right? So this is just defining our variables, right? Defining the parameters, and these are, yeah. So you notice that we structure the so this is the A is the matrix and B is the vector, right? So yeah, so this is what it looks like. This is just printing vector A, and you notice that we structure the coefficients into the matrix A and the constants into vector B, right? And you understand this like translation that's going on over here is important because we have like millions of equations and we use matrix to represent them in a very compact manner, right? So this is the equation that we come up with: 5x plus 2y equals minus 2, which is just the top, right? Minus 5x
Hello.
plus
Hello.
2y. Hello, yeah.
Sorry, I didn't interrupt you, but I just have a one question. Please, when you move up,
Okay.
you the presetting that you did on the print setup and those things, yes, set a print option. Does it affect the next line?
Yeah, it is going to, anytime I call any NumPy library or any NumPy function, it's going to
Yes,
follow
please.
this. It's going to follow the configuration I've done over here. Anytime I
Mm,
call any
okay.
NumPy library, it's going to,
So,
yeah.
please, the precision is what?
The precision, the precision is just so it prints like numbers cleanly. They are setting it to four to get four decimal places. It's just decimal places or yeah, decimal places. So I'm setting it to four decimal
Uh-huh.
places. Yeah,
Okay. Okay. Thank you.
yeah. Okay. So over here, I just define our parameters A and B. A is our matrix and B is our vector. Right. And let's go on in. So let's see how, I think the last time I met you guys, we did the determinants, but then this is also, let's just do it over here too as well, right? So before we solve the system, we need to check if it has like a unique solution, and that depends on the determinant of the matrix, right? So the determinant tells us whether the matrix can be inversed or like it's invertible, and whether the system also has a unique solution, and also the scaling of and the geometric scaling and orientation change that the matrix can apply. So if the determinant is zero, we can say that the system either has no solution or it has like an infinite number of solutions. And if it's non-zero, it means that the system has exactly one solution. And this is how to calculate the determinants. If you are doing it numerically, we have your matrix A, B, C, D. Taking the determinant is just A times D minus D times C, right? So for a 2 by 2 matrix, that's how it is done. And so with NumPy, all you need to do is to call the this dit function under the linear algebra library in NumPy. And then once you do that, you pass in the matrix you want to find the determinant of, is going to do the calculation for you, and you get your matrix, right? So that's what I'm doing right here. You print the value of this calculation, the value of the det A over here, as an F string, right? And then we also check if a unique solution exists using this np.isClose function. So what it's doing is just checking if the value of the determinant is zero. If it's close to zero, and we get a boolean output. So technically, this is the function, right? np dot is close, right? If that's the library, np dot is close. So we check that this determinant, whatever value we get from this variable, if it's close to zero, then it should say true or false. And if it's not, it will say, if it's close, it will say true. If it's not, it will say false. But we want to check if the value is not close to zero, because that's when the unique solution exists, right? The unique solution is going to exist when the value of the determinant is not zero, right? That's why we have this. So it's just the inverse of it. So if the value is not close to zero, then the unique solution exists, and that's what we have over here. Okay, so that's what we're doing over here, just checking the determinants. And once we have a unique solution, we can go ahead and do the calculate the systems and all of that, and we are sure that we'll get actual values, and we'll not be getting like we are sure that the system has a solution so we can solve for it, right? So there's a little visualization over here, just to visualize what the matrix A does geometrically. So any 2 by 2 matrix transform in the unit square into some parallelogram, right? Any 2 by 2 matrix will transform your square, a unit square, into some sort of parallelogram. So what we did here is just to get a unit square. This is a unit square, a square with the sides equal to one, right? All the sides are equal to one. So that's what we did over here. We just got the points 0, 0, 1, 0, 1, 0, 1, and 0, 0, and it just like draws. So it starts from the beginning, from this point zero, starts from point zero, goes to 1, 0, comes to 1, 1, comes to 1, 0, and comes back to 0, 0. That's why you have 5 points, but it's a square. Starts from here and ends here, right? So with that square, when you apply the matrix transform, you apply any 2 by 2 matrix to transform it. The area of that parallelogram that you get is the absolute value of the determinant. Okay, so here we use the matrix A, right? And matrix A is what we are working with, which is -5 2 -4 1, right? So as you can see over here, we just apply the matrix multiplication of the unit square that we have with all these points times the matrix, right? So that this acts is just multiplication, matrix multiplication. So no matter what kind of whether it's a vector, it's a matrix, or anything, it's going to apply do the multiplication for you, or just using this at sign. Yeah. So going forward, we'll be using that for all the matrix multiplication. Okay. So that's what we're doing. So we just specified our unit square over here, and then we apply the transformation using we applied this matrix to transform it, and then just to visualize what happens. So any 2 by 2 matrix will just transform the unit square into a sort of parallelogram, and this is the parallelogram that we get when we use the matrix A, right? And then the absolute value, or is the area of this parallelogram is the absolute value of the determinant, which is 3, right? So yeah, and yeah, so this is what it looks like, right? And this like helps you understand what a determinant actually means, right? It measures how much the matrix stretches or squishes, right, in space, and that's what we have, right? So let's go on and do the and do the and solve for the system, right? So the first approach that we'll be using is the Kramer's rule, which is just the ratio of determinants, right? So it's not really used much in real computation because it's not really efficient for larger systems. But then, if you want to understand, if you want to for understanding and intuition, it's very useful when it comes to that, right? So it explains how determinants relates directly to solving equations, and shows how it also shows how when you replace a column with a target vector, it gives a corresponding variable. Okay, so even though we'll not be using it for large systems, we're just going to use it to understand, right? Okay, so let me go on to so this cell is doing the Kramer's rule calculation, and as you can see for our first, this is for x, right? So A1 is X. You can use X. Right? So for X, we are going to replace the first column, right? So first column is 0 with our vector B. Okay, so copy A dot copy is just going to copy the first. A dot copy is just going to swap these two, right? So it's just taking the first column over here and then replace it with a vector, and it has the same dimension, right? My first column is 1 by 2, right? And then my vector is also a 1 by 2 vector, right? So it's just going to swap them and do same for the y as well. Take the second column for the y, right, and swap it with the vector. I think this was done in the theory class, so you can get a hang of what's going on over here. And we take the determinant of each modified matrix, right? So this first one is a first modified matrix, and this is a second modified matrix. So we take the determinant of the first one, right, and divide it by the determinant of the original, and we do same for the second one and divide it by the determinant of the original. And as you can see, this is what we for the first one we get 2, and for the second one we get 4, right? So that's where just doing replacing this formula. It says X is the determinant of your modified matrix A over the determinant of the original, and then the modified is just replacing the the vector with the columns of the original matrix, and then find the determinant of that, and then by there. So this is like a direct mechanical approach. Just it's impractical for large systems because you can't do them. You can't do it. If you know this, this is just to understand how it works. But then in actual systems, we have a larger matrix, and you can't be doing this for all of that, right? So it's generally it doesn't work for large systems because determinants become like difficult to compute repeatedly, right? So that's one approach, and then the next one is the matrix inverse, which is like the 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 layman's way of approaching it, right? So we have that our equation was ax equals b. So if you want to find x, it's just change of subject, right? So x is equals to b over a, or the inverse of a times b, and that's what we have over here. So we're just trying to write this in code, and then right. So first thing we need to do is to, because we already know a and we know b and want to find x, but now we have another unknown, which is the a inverse. And how do we find that? It's just the with NumPy, all you have to do is to call the function. So we want to find the inverse of a, and we are using the linear algebra library. So this is constant. All you'll be changing is what you want to find, right? So you realize for determinants we just use that, and now for inverse you use I and v, and then you pass in your matrix that you want to find the inverse in, and then we store it over here, right? So this is it's the a inverse. This is what a inverse looks like. So a inverse is based on the calculation 0.333, 0 point minus 0.67, we have 1.3 and minus 1.67, and this is the inverse of the original matrix A. And then the next line is doing the it's just computing what we have. So we want to do the inverse times b. B is our vector that we already have. So doing that, you get a vector as an output, right? So x and y, and then you compare it to the Cramer's rule method. We still see we got the same value, 2, 4, and same thing over here, right? 2 and 4, and this is like straightforward, right? This is a bit straightforward. All you have to do is to find the inverse of the matrix you want to do. You want to work with NumPy. It's simple. All you do is just pass it over here in your inverse library, in your inverse function, and then you compute it with matrix multiplication, and then you are good to go. Right. Okay. So there's another approach, the Gaussian elimination, which is essentially LU decomposition with partial pivoting. LU stands for lower upper. So it divides our matrix into a lower triangle and upper triangle and decomposes them, and then applies some pivoting to solve for the x and y to solve the system. And this is what the NP dot linear algebra does solve. That's right. With the LP dot linear algebra, that's the best approach to solving. We'll see how that works, but then we'll use that to see the outputs. But then this is how it works. Right? This is how it breaks it down. Okay. So for here we have our LU factor. So there's some imports over here. Import said linear algebra from SciPy, and just because we wanted to use the lower upper factor functions and the lower upper solve function, right? So here, this LU factor from SciPy is going to perform an LU decomposition on the matrix A using the partial pivoting. And what that essentially means is that the Gaussian elimination is going to happen behind the scenes. It's going to break the matrix A into the lower triangle, upper triangle, as I said. But instead of returning the lower triangle and upper triangle separately, SciPy is going to store them together in a single variable LU. Okay, so this LU factor is going to do the separation of the matrix over here. It's going to do the Gaussian elimination and all of that, and it's going to store it over here for us LU. And then the second output, which is the pivoting, will contain the pivot indices. That's the rules that will be swapped during the elimination, right? Just to ensure that it's stable numerically. And then we pass the results onto this line, and that's where the actual solving is taking place. So the whole workflow is just factor the matrix once, break it into lower and upper triangles with pivoting, and we use that factorization to solve the system. So LU solve takes in the LU values and the pivot values, and then we add our vector B, our target vector, right, as we defined in the beginning, right? Then it's going to do the substitution for us, and then we're going to get an output. So when we check the output of x underscore LU, we get 2, 4, as you can see over here, right?
Hello.
Yeah, hello.
Yes, please. The LU command the pivot, what's the value for it, please?
The value we can't see it over here because this is doing the calculation for us. The LU underscore factor is doing the calculation for us. So whatever value we have here in our matrix is going to do the calculation and store them over here as LU and PIV. And I was saying that the LU is the division, the lower triangle and upper triangle values, and it's going to store them as
Mm,
LU. And the second output, this PIV, is just containing the pivot indices. That's the
mm,
rows that were swapped during the elimination,
mm.
right? But what the exact values are, I don't know. And that's the computation was done with this LU factor function. Okay, that's the
Okay.
computation was done over here, and it's just storing here for us. And then all we had to do is just to call them in over here. That is substitution in the LU solve function. So if you check the documentation for LU underscore solve, you need to pass in your your LU values and your pivots indices values and the target vector, and it's going to do the computation for you, and you get your x and y values over here as a vector. So that's what we did over here, and we got the value. So this is the first print. We print the solution via lower and upper triangles, and this is the value that we got. And we just compare it to see. I mean, but we can just go back to check. But then the second line is just to compare to see if it's same as the linear dots algebra dot solve approach, right? So this approach is the simplest, the best way to do it, right? I think it's down here somewhere, right? So this is linear, the linear algebra dot solve approach, right? All you have to do is pass in your matrix and pass in your target value, and it's going to find x for you. It's going to automatically find the determinant, do the computing for you, and with just one line of code, it will solve your x and y values for you. You don't have to do the change of subject and find the inverse and find determinants to be able to work with it. But all you have to do is define your matrix, define your coefficients a, and define your constants, and then it's going to compute the variables x and y for you, right? So that's the standard approach for solving a system of linear equations. Yeah. So over here, it's just a couple of the other methods that we have available. This is the NP dots linear algebra solve, and it's the fastest generally, and most ML libraries use it. Almost all of them use it internally because it cuts off the time to compute different lines of code and all of that. And this is the least square method as well. We didn't do that here. I'm sure maybe it will come in an assignment. That's why I wasn't put here. But then it's also very helpful for regression cases and all of that. And we have the LU decomposition. There's a Gaussian elimination method. When you have multiple B's, multiple target values, you can use that. All you have to do is just to substitute them over there, and that's the competition for you. So we'll share this notebook with you. You can just go through and see how the pros and cons of all of them. Right, and this is just a few. There are others as well, but then just what's relevant. And yeah. Okay. So right. So these are examples to try your hands on.
Hello.
Yeah. Hello.
Please, I didn't interrupt you. Please, are you done with are we that's all we have another
Sorry.
I was saying that okay. Please, with respect to the Kramer's rule,
Yeah.
the Kramer's, yes. In which application can we use it? The Kramer's,
As for
yeah, the
Kramis,
Kramer's rule.
it's more of just teaching how how it works. How it's just teaching, just giving you an intuition of how the determinants are related, so you can how the determinants of a matrix are related to find the x and y values. But practically, it's almost never used because you then have to find determinants of everything and substitute the columns to find determinants again. So it's almost like never used because it's a whole lot of computational power that you need to that you need to that you need to run it. So almost never used. Actually, if you realize here, you have to find the determinants of two forms of three forms of the matrix itself: the matrix in its original state and the matrix with each column replaced. So if it's a 3 by 3 matrix, you have to replace all the columns and find the determinants. before, and then you come and do the division of them one by one to get your x, y, and z values. So it's almost never used. I can't think of any use case like practically right now. But then generally, no, no, no. You maybe perhaps if you want to find one variable like just a y, but still the yeah, almost never used unless you want to explain how the determinants are related in that sense, and then you just yeah bring it up. But then yeah, I don't know if I answered your question well.
Yes. Yes, please. Thank you.
Okay, okay, all right. So where am I? Where am I? Yeah, this is just a demonstration to show why we never use the index. So if you realize in the table over here, it says that the solving with the inverse is like exterminating ants with a nuclear bomb. It's also almost never used because it's like a very complicated way to solve a little problem. So this is like a demonstration for why we never use it in practice, right? So what's the Hilbert's matrix? It's just a classic example of an ill condition matrix, right? It means that any changes, any small change in the inputs can cause a huge change in the output, and then practically it makes it very hard for computers to solve them accurately. So what we are doing here is just to generate a 10 by 10 Hilbert matrix here. So n is just specifying the number of rows and columns. So this is a 10 by 10, and the Hilbert matrix is what we are calling it by. It's like a known function, a popular matrix. So SciPy has a function that when you just call Hilbert is going to generate a Hilbert matrix for you. All you have to do is specify the rows and columns. That's what we did over here. All right. So n is just the number of rows and columns, and then we can choose the exact solution to be. We are constructing a system with a known solution, right? So we already know that we want the true solution of the vector to be all ones, right? And then we compute the right hand side, which is b, right? The equation is ax equals b. So b is equal to a times x, right? So we already know our x values. We want to find what the b will look like with the Hilbert matrix. So we do the matrix multiplication, and using the inverse approach, you have to just do the linear algebra. That's the change of subjects approach, as I said earlier. So your x is just the inverse of h times d, right? And same for y. Yeah, so this is using the so once you do that, you get you get a vector as your output and to contain your x and y parameters. If you say to if you're just solving for x and y, if you're solving for x, y, z, you will get it as well. So this is using the inverse approach, and this is using the linear algebra to solve approach, which is like the recommended one. All right. So just right. So this is just to you see we already know the answer. You already know the solution, right? So this is just to to find the degree of error. The what's there? Well, just to measure the damage. I think measure the damage is the right way to. So just to measure the damage or tell to see how unstable the matrix is, right? So the condition number of a Hilbert matrix is just telling us how unstable the matrix is, right? And yeah, it's just going to tell us how unstable the matrix is. So for a 10 by 10 Hilbert matrix, the condition number is like very large, usually 10 exponent 12, 10 exponent 13 ish. So that's what we have over here. We have 1.6 times 10 exponent 13. Just shows how unstable the matrix is. And so for the inverse approach, we are checking the errors, and the error using the inverse, as you can see, is like larger as compared to the solve approach. Using the inverse, we get 2.2 times 10 to the power minus 3, and using the linear, we get 1.32 times 10 to the power minus 3. So the whole idea is, even though like you get the same answer, but for a matrix that's it's like complicated, or it's like it's not really conditioned well, you are going to get as are going to the matrix inverse is going to like amplify the numerical errors. It's going to give you a less stable value, right? You're going to deviate completely, and you wouldn't know because you don't know you wouldn't know what answer you're supposed to be getting, so there's no way to check, right? But then, yeah, this is just to show. So with LU decomposition is, yeah, right. So this is also a visualization to visualize the solution to our 2 by 2 linear system as the intersection of two lines, right? So we're just going to this is our vector, the matrix and the vector that we are working with, but represented in equations. In equations, y equals mx plus c, and you can already tell the vectors from this. Our vector was -5, 2, -4, 1, and x, so that times x, and then our b was -2 and -4. So we just represented them as lines and then plus them. So you realize that the points at which they are intersecting is our x, right? It's our unknown vector, and you can still see that it's intersecting at the points 2 and 4, right? So visually, you can also solve a system of linear equations visually by just plotting them and finding the points at which they intersect. Okay, so that's also something little to let you understand what's going on. So yeah, so the next thing is just to delve a little bit deeper into the linear regression system of equations. Kindly give me 10 minutes to do something quickly. I'll come back and call back to continue. I think a little over, we have 45 minutes ish, so I'm sure we'll be able to finish, and then I'll touch on something briefly. So please give me, I think 6 minutes will be enough. So let's take a break. 6 minutes, we'll be back. Okay.
Yes, please.
Okay. Great. So this is the last part of the notebook, which is the linear regression. Trying to come up with a line of best fits and all of that. So we think we'll do with the linear regression, with a linear equation, and also with the polynomial, yeah, with the polynomial regression as well, and try to get why we include the intercept column as the columns of one year design matrix, right? So let's start with a normal one. So this is our equation that I'll be working with, and this is the points that we are going to plot, and then we'll find the line of best fits through those points, right? So points A is 0, 1, points B 1, 2, points 3, point C is 2, and 2.5, right? So we separate them into x and y components, where x is 1, 0, 1, 1, and 1 2. Anyone explain why x is looking like this? I mean, with y you can already see that the y is 1 2 and 2.5, which is done over here, 1 2 and 2.5. All right, but with the x we're having this in pairs, almost like x and y again. Anyone wants to try? Okay.
Hello.
Yeah, yeah, Daniel.
Yeah, I think it's because it was 3 by 2 matrix, and then the other one was 2 by 1 matrix.
No, this one is away from the matrix. We are starting like almost fresh, but we are trying to this is our target point that we are trying to plot. We are trying to plot 0 1 1 2 and 2.25. But then we are sort of designing our matrix ish. So it comes in pairs like x and y, x and y's. But here our
Uh,
x is already in pairs. It's already coming as x is 0, 1, and 2, right? And if you
yes,
check this
yes,
part of the if you check this second part, so I guess this is 0, 1, and 2 for our x, right? But
yes, yes.
we have these ones over here, and I'm asking if anyone can like try and explain why we are doing that over here.
Okay. The
Hello,
the yes.
hello.
Yeah, hello.
Okay, so please, we have the one over there to prevent the transformation from passing through the origin.
Mhm.
Yeah, yeah, yeah. I mean, basically, exactly. Yeah, that's why. Yes. So, yeah. Sorry, give me a second. Yeah. So that's why. And as our equation over here is what x exponent tx times theta equals exponent x exponent t of y, right? So the first part, which is x exponent t times x, is just computing the matrix transformation. So of this and this is just going to multiply this and this, and I'm going to do the same for the y aspects over here, right? So we're going to solve it with the linear algebra solve, and it's going to do the calculation explicitly without actually taking the index, which we proved up here that it's more numerically stable as compared to having to take the inverse of it, right? So that's what it's doing over here, and then we we do the go ahead and do the printing and all of that. So this is the design matrix, which is just to prevent a line from passing the origin, as Richard said. Right. So during the calculation, we get a line of best fits to be 1.08 and 0.75. Right. And with this line, it's you see the line of best fits, or it has like it's not absolute values. They are flutes, they are decimals, they have like a little bit of noise in it. So it will be difficult for your line to pass through the points exactly. So we're trying again with a perfect line in quotes, right? Which is y equals 3 plus 2x, right? Y equals ms plus c. We know mx, which is 2. So 2 is our intercept and 3 is our slope, right? And then this is just a different set of points where x is 0, y is 3, x is 1.1, y is 5, yeah, go so and so 2, 7, 3, 4. So it's linear, like it's linear, and then so it's like it's a straight line, right? And we also won't forget the design matrix over here, which is to prevent the the line from passing through the origin, the intercept from passing through the origin. So we just stack a column of ones at the x side of the x axis of the x data. Right. So the first column will just be ones, like we did here manually. This time we are doing it like in code, so that as we continue to add our values over here, we don't have to come and add ones as we go. It's just going to automatically do it for us over here, and do the same computation over here with the same equation, this equation, and get the intercept over here. So as you can see, intercept is 3 and 2, which is like more exact as compared to the values we had in the first one. So this there so the with the intercept column, the column of ones, that's just to allow the model to learn a y intercept bias term. And without it, the model is forced to pass through the origin, like, and we just include it so that it takes shape of the original real data, right? So that the prediction that it gets is not going to be biased. Okay, so the first one, the red line is without intercepts, and as you can see, it's trying to pass through this or the origin 0 over here. Right, it is like a computational error, a computational glitch when you're using linear regression. You always have to like design your matrix such that you design this so that it doesn't fall prey to the y-intercept bias. Okay, so you generate a column of ones, you add a column of ones, or you design a matrix to have a column of ones, and then it's going to get you the best line, the line of best fits more accurately based on your data. Right. So we can we can find the best linear or approximation to a set of points, and this is like just illustrating how linear regression is just solving a linear system. You're trying to link the geometry and the algebra and the data fitting. Right. So we yeah. So this is an example of a point where the example of a point where the points are lying exactly on a straight line, just for you to see the mechanics of linear regression when there is no error in it. Okay. So the key thing is the design matrix over here, which this approach works for any number of points and dimension, right? Any number of points and dimension. All you have to do is to write your points normally, not hard coding it like this over here, and then we add a column of ones just to ensure that the y-intercept is included. If you don't do that, it's going to be biased towards that. And in a perfect linear case, the regression will exactly recover the original line. And generally, this method, this is this method like generalize easily when it comes to multiple features when you're doing multivariate regression and and stuff like that. Okay. So the next thing, the visualization over here. Yeah, so let's talk about the polynomial regression. Yeah, so let's see what happens when we try to fit a quadratic model to a data that is actually perfect. That's like linear, right? Perfect linear. And this just helps us to understand how flexible a model is, and also how higher degree models behave. Okay, so we first off build our quadratic design matrix, also almost like the same principle of the linear the linear matrix, where we just include a column of one. So what we do is to create a column of ones, which is the intercept term, and then we have our x data, which is I think I don't think we got the equation by, but it's going to be theta one. So with the quadratic is I think for a line is y is equal to mx plus c. Quadratic is a x squared plus bx plus c, right? Yeah. Let me see if right. I think it's ax squared plus bx or by plus bx squared plus c, right? Yeah, ax squared plus bx plus c equals 0, right? So what I'm trying to say, so our c is our intercept term, so that's our column of ones, and then bx is our x data, and our quadratic term, that's the ax square or the x square, is that x data exponent 2, right? So this is us building building our quadratic design matrix, right? And then we we go ahead to solve for theta, right? Go ahead to solve for theta using the linear algebra solve function, and all we have to do is just pass. We are solving using the least squares normal equation that we have in the first one. This equation, right? Solving using this equation. Okay, so even though it's a quadratic model, the system will still solve cleanly, even though we are using the normal equation that we use for the linear model, right? So as you can see over here, quadratic fit, and then let's plot it over here to see what it looks like, right? So the blue line is the linear model, the linear fitting of it, the best line, the line of best fit by using the linear model. And the second one is the quadratic fit, which you can see is almost, I mean, it's for a line of best fit is almost perfect, but then it's still the same least squares normal equation that we use for the linear model. And you realize that the system like is able to still generate a line of best fits for a polynomial, for a quadratic function, right? And if the true relationship is linear, a quadratic model will naturally set the x squared coefficient to 0. As you can see over here, our x squared coefficient was 0. And it explains like two powerful concepts. Over parameterized models can still find the correct function, and also using the least squares also automatically identifies unnecessary terms, right? And extra parameters will not necessarily harm the fit if the data is perfect. So if the data had lots of noise, the second that's theta 2, the x coefficient, might slightly become non-zero, and that will open the door to overfitting and stuff like that. But with these working with linear regression, once the the relationship between the two models are linear, the the quadratic model will automatically set the x square component to zero, and then to be dealing with it as if it's a linear, like as if it's the y is equal to mx plus c, because your x squared term will be equal to zero, and you still get you still get a correct prediction, you still get a correct curve, and that's like a way that overfitting and all of that is checked when you're working with real world data. When your data is too small and your model is like learning it and over learning, or it's overfitting your parameters, it's what you can tweak it, you can tweak your code to set or to ignore the unnecessary terms, right? And it's automatically going to do that, and then gets a better prediction of it. So that's, I think that's about everything. This is a summary of everything that we've done so far. Don't stress yourself with all this code. It's just plotting. You can go through it later on your own. But yeah, I hope this is big enough. But yeah, so the first thing we did was doing the transformation on a unit square. Right, so if you have a unit square and you transform it by with a matrix, you apply a matrix to the transformation, you get something that looks like a parallelogram, and the area of that parallelogram is the absolute value of the determinant. And we also see that the second one is lines, two lines intersecting. The point at which they intersect is the solution. It's how, what's driving. Yeah, so when you're trying to solve a linear system, you can plot them as two equations or two lines, and the part at which they intersect can be termed as that point, that part is the unknown, that part is the x value you're finding, which comes in x and y values, right, for a 2D space. And also intercepts of a linear equation. We include the column of ones to avoid the y-intercept bias, and you realize that the column, when you don't have the ones, the line of best fit is forced to pass through the origin, and once you include the bias and it takes that into consideration, you get a line that you get a better line that passes through the actual points that you want. And same for the polynomials. If you have a quadratic equation, your linear your linear function can still do the prediction for you, because if the relationship between them is linear, or if there's a correlation between your quadratic function and your linear function, it can automatically throw away the unnecessary terms and then do the plotting for you, and whatever extra columns you have will be thrown away, and you still get the line of best fits to work for whatever function that you have. Okay. And also, this was what functions that you can use in when you're working on real life, on real world ML code. Yeah. So, oh my god. Right. So the most recommended approach is the NP.C, linear algebra dot solve function, mostly because it's the most stable to use, the most the fastest, and also the most stable, because it doesn't take the inverse of it. It doesn't take the inverse of the matrix. it does the computation explicitly without taking the inverse. And as we proved, it's the best approach to use as compared to the inverse approach, which might seem like the most logical approach to use when you're finding your x in your service and all of that. And you can also use the lower and upper triangle for more advanced tasks. With that one, if you have a lot, you have multiple bees, multiple targets, then you want to find, you can use that, or you can then you write a function that will just be swapping it and all of that. And for regression, we use the least squares approach. And for this, the regression part that we're using the least squares approach, right? So for regression, that's like the recommended one to use in practice. Okay, so these are some exercises that you can try on when you get the notebook. And I think that this is where we end. So this one was short. I hope I explained a little bit clear and it was okay for you. I'm hoping. I think with next week's session where we have to do a practical next week's session where we'll be doing a practical how do I call it, a more practical approach to the whole thing. It will be easier to explain, and I mean it will be easier to understand how all of these things apply in actual ML, actual machine learning projects and tasks, right? So one, I think says I'm done over here, but if you have any question, let's see any question from you guys. Hello guys, are you here? Okay. So I wanted to, yeah, hello, yeah, I'm not sure if I get what you mean. Oh, okay, okay, yeah, 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 yeah. No, no. So um, it just has to have a connection. You can use you can use multiple times the x exponent, and you can use x exponent 3, x exponent 4. Doesn't matter, any polynomial at all is going to be able to predict the line of best fits. Yeah, it's going to be able to do the prediction as it goes. But then if the model is not able to do the prediction well, then you will be able to tell whether it's overfitting or it's not. Um, what it does is that it's going to like throw away the it's going to set the x square, x exponent 3, x and then 4 times to 0, and work with the linear part of it, which works in some cases, but then in some cases you realize that it will be like doing the prediction way out of the space that you want it to. So it depends. It depends on the least square equation you're using, and it depends on the equation of the polynomial that you want to fit it on to. Yeah, but this was just like a demonstration of how the linear the linear function can be used to be fit can use to fit a quadratic function. I don't know, maybe probably in the assignments they would ask you to do something like that, like to fit it on a polynomial with a different with maybe three x exponent 3 times or something to a third degree or something. I don't know. But then yeah, I hope this is I hope I answered you. So and in which situation can you use when you are doing ML? Oh, in so it's one of the ways to train your model when you want to predict like a continuous numerical value, or like you believe that there's a linear relationship between your input and output. This is like one of the most popular and also simple supervised learning algorithm. And as like we demonstrated with this with what this small thing that we do over here, you realize that even though it was initially designed to work on a linear equation, it also performed well on a quadratic equation. So mostly when you are just trying to do comparisons of trying to get a linear relationship between two 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 systems, or two system, you can use the linear regression to do that. But it's a predictive model. So most of the predictive tasks, say for forecasting, prediction of based on your data set, you can use linear regression to like just predict what will happen when some variables are kept constant. So it's more of a predictive algorithm. So anything prediction, you can use linear regression. And they are like I think there are two types. There's a simple linear regression, there's the multiple linear regression. Single linear regression, just simple, just works with like trying to predict maybe someone's salary. Let's say you want to predict someone's salary, and you want to predict it based on their years of experience. So it's just two stuff that you're like working with. So so you have a data set of lots of people's years of experience and their salary, and then you want to predict if this person is has this years of experience, what will be their salary. This is like just two variables that you're working with, right? But if you but the multiple regression, when you have like multiple factors, maybe you want to add the person's education level, you want to add the industry. So like that will also like improve the prediction. So like basically for prediction, right? So any predictive model, you use linear regression a lot. Right, linear regression is really used a lot. Yeah, yeah. Yeah. Did that help? Yeah, yeah. I wanted to talk about the convolution, the image thing that I had to explain a while ago. I wasn't able to. Let me see if I can pull something up online. Yeah. So the last time, I think Richard should be more conversant with this because we thought this last semester. I'm going to share this. Right. So I think last time you came, I was trying to explain this thing, how images are represented as pixels. Right. So as you can see, this is the image, the 2D image on the left side, right? And the grid is just to show how pixels they're like they are way smaller than this, but then this is just to show them pixel by pixel. So each pixel is represented with a matrix value for for 2D images or for grayscale black and white images or images in general. It's just in intensity values from zero between 0 and 256, right? So 0 is black, so 0 being black and 255 being white. So it's just ranges of all of that. And I also explained that with the colors, it has RGB, so it has intensities of all these different channels. That's red, green and blue, and all of that, right? So that's like how images are represented, can be represented as matrix. And I was explaining how convolution is done. I'm going to share this. So this is something called convolution. You can, I'll share this with you. I'll share the link with you on WhatsApp so you can just get an idea of what it's like. So it just takes two matrices and merges them to get a third matrix. Right? That's convolution. It's almost like the matrix multiplication, but it has a little twist to it. It's not exactly like the matrix multiplication, but it has a little twist. It's just like that, but it has a little twist. So the original matrix, that's the original image, is your input matrix, and then you have a kernel or a filter. That's how image filters actually work. Blurring, sharpening, most filters, that's how they work, right? So you apply the filter onto your matrix, and then your output is your feature map, right? So it's like it's some mathematical operations that goes on over there. It takes, so this is our kernel, right? 1010, a 2 by 2 kernel, and this is our matrix. So it does the convolution over here. So it takes this kernel and places it on the matrix, and slides it like step by step. So 1010 is going to fit on this 2 by 2 part of the matrix. It does the convolution, and whatever value that it gets will be the new input of the feature map of the new matrix that will be formed. Right? I don't know if there's something here. So as you can see here, so our kernel is 1010, right? It's going to be placed over here. Then it does the convolution computation, and then the output is stored as a new pixel for the output image that we get. And then we move on to the next part, do the computation, and we get the next. So yeah, I think right, right. So that's the computation. Go on to the next one, the computation, and then we come back to the down, do the same thing, get the value, go on, do, and then you realize that at the end we get a new matrix, a new image that's being formed with different intensity values, and then based on the pixel value that we used, we are going to get like something different on the original image. I didn't have to, I couldn't, unfortunately I couldn't, maybe I'll include like that's, I don't know if it's I don't know, perhaps I have a notebook on that. I can just share it with you so that you can see like it's in you can see it's in effect, right? So it just so if the kernel you're applying is say how do you call it? It's a mean filter. You are going to get a blur effects on the image. It's going to blur the image to some extent. And if it's a sharpening feature, it's going to sharpen the image to some extent. So that was what I was trying to explain, like the practical use of matrix when it comes to data science, when it comes to machine learning or deep learning, if you want to call it deep learning. And yeah, I don't know if this also helps, but like this is what I wanted to explain that we got cut off. I think Richard understands this part, so no sure. But Daniel, is this okay? Do you have any question? Should I clarify anything for you when it comes to that? Yeah. So yeah, I think then we think that we've covered everything that we have to cover for this lab. I'll share the notebook right after here so that I don't forget. I hope you're able to get last week's notebook though. Were you able to get last week's notebook? Okay, okay. So I'll share this one. All right. Just when this class ends so that I don't forget. Yeah. Okay. Yeah. Hello, Richard. Ah, through Canvas, through Canvas. I'll add you so that you receive it. I think you're not in my group, but I'll add you so that you receive it. Yeah. No, no worries, Chief.